This is meant to help you understand how RSA encoding and decoding works. So, roughly speaking, two-step process. The first step is to encode using this relationship. Basically, you raise to the power e on the plain text p, and then you get the ciphertext. To decode, you simply raise to the same to another power d, and on the plain ciphertext, then you recover the plain text. And so, just these two-step process. They're both raising to some power. One is e, the other one is d. What's the relationship between e and d? They're inverse of each other, mod phi of n. E and n, they're made public. And then when e and n are made public, you probably don't need to worry about other people will be able to figure out the d, because it's very difficult when the n is large and then two primes are large. It's very difficult for us to figure out which two prime numbers are used. So it is very difficult for us to figure out these two prime numbers. Then it's even therefore it's difficult for us to figure out phi n. So without knowing the phi n, it's difficult for us to find the d. So that's why this d is kept secret, is private, and it is difficult to find. So even though you are given the C, which is the ciphertext, if you don't know the D, you have no way to decode, to recover the plain text. So this is the idea. Now I would like to show you how to suppose our plain text is 1520, and then the ciphertext will be 1520 raised to power 13 in this case. So we are using the 13. And then now how do we compute that? Different ways. This will be a little easier because this 13 power is pretty small. I would like to show you how to find the residual when this is larger, much larger. Here this is 937, and where's the 937 from? It is coming from you have to find the inverse of the e from this linear congruence. And usually I would suggest you at least one way will work for sure is this. So let's take a look at this one. So 13d congruent to 1 mod 2436. You can convert it into linear Diophantine equation. 1 minus or plus or minus doesn't really matter. Here I'm going to choose the minus 2436k, which means 13d plus 2436k equals 1. We do know these two numbers, 13 and 2436, are relatively prime. That's how we choose the e, and therefore the greatest common divisor is 1. This is the linear Diophantine equation. Basically, you want to use Euclidean algorithm and then write the greatest common divisor in terms of the linear combination of 13 and 2436. So I'm going to skip that. The answer is 937 here. 937. So if you need to review this, you don't know how to do that. So Diophantine equation is what you wanna review. So my focus is so usually the next step. So to encode 1520, we just 1520 raised to power 13 mod the n 2357, and which is 95. So again, I'm gonna skip that because this is much harder. if you know how to solve this, you should know how to do that. So how do we recover the P? So from the 95, which is the ciphertext, you raise to the power D, which is 37, mod 2537. So let's look at how we are going to do that, okay? Basically, we are going to take advantage of the Chinese remainder theorem. This 2537 is equal to the two numbers we picked was 43 and 59. This is what we want to figure out. We want to figure out 95 raised to 937 is congruent to what? Mod 43. And then also the same number, 95 raised to 937 is congruent to what? Mod 59. Because I did this in class, did the first part in class, let me focus on the second part first. So call this as your x, right? Let's call this as your, this actually is your x. Basically, I'm going to try to find x is congruent to a1. I need to figure out this guy. X is congruent to a2, mod these two different numbers. 59 here. Then this is actually the Chinese remainder theorem can solve this system of linear congruences. So at the end, you find a unique solution. X is congruent to, you will find this solution, mod 43 times 59, which is actually 2537. So that's the idea why we want to use the Chinese remainder theorem to solve this one. Otherwise, at least one method that you already learned was just throw it out here. If you can remember fast modular exponentiation. So usually this method works very well when this is big and when this is big, when they're both big. So that's another alternative way to do that, and it should work just fine. So here I just want to more focus on the Chinese remainder theorem. So I'll begin with the second part here. So first of all, I want to reduce this 95 because we mod 59. So 95 mod 59 is 36. 937. Now this is congruent to here we do know 36. So 36 raised to 5 of 59 should be congruent to 1 mod 59 according to the Euler's theorem. And 59 is a prime, which means 36 raised to 58 should be congruent to 1 mod 59. So I just need to figure out how many 58s are in the 937. It turns out to be, this should be just equal sign. I don't have to use congruent sign here. So 36 raised to, there were 58 of, 16 of 58 there, and you're left with 9, okay? Which means 36 raised to power 58, and there were 16 58 there, times 36 raised to power 9. And this is congruent to 1 according to this Euler's theorem. So we're left with 36 raised to power 9 mod 59. Okay, I'm gonna do a little algebra right here. Because we do know 36 square, you can do this algebra. This is congruent to -2 mod 59. And therefore 36 raised to power 2, and then let's raise to another power 4 here, which is 36 raised to power 8. Is congruent to -2 raised to power 4, right? So this is 16. mod 59. Oops. So therefore, from here I do know that this will be 36 raised to power 8 times 36. And this is congruent to 16, just like what we said, which is 16 times 36. And this is congruent to 45 mod 59. Okay, so therefore this is going to be 59. So I'm going to write this here. This actually will be 59. And in class we did do this part. This is 15. You can use the same idea. This is 15. We did that in class. So therefore, basically, this is what we have. This is 15. This is 59. Let's call this as the first equation. First linear congruence. This is the second congruence. So from the first one, we know that x is equal to 15 plus 43, let's say t. And then plug in the second one. We're going to have 15 plus 43t is congruent to 59 mod 45. That's incorrect. That's actually, this is not 59. This is actually 45. Sorry about that. This is actually 45. That's what we solved right here, right? So this is actually 45. So therefore 45 mod 59. And subtract both sides by 15. We have 43t congruent to 30 mod 59. And 43 is congruent to negative 16t mod 59. And I want to divide both sides by 2. So therefore negative 8t equals congruent to 15 mod 59. And I like that because now I can multiply both sides by 7. And then if I multiply this by 7, so this is negative 56, negative 56 mod 59, which is 3, right? 3t congruent to 15 times 7. Now I want to divide both sides by 3 now. So t is 5 times 7, which is 35. So now, therefore, according to this result, I'm going to plug this in here. So x is congruent to 15 plus 3 times t, 43 plus 43 times the t, which is the t is 35 mod 59, right? So which means t is equal to 35 plus 59k. So I'm gonna 35 plus 59k. Okay, finally we are able to do this 15 plus this will be 43 times 35 plus 43 times 59k. So it turns out to be 1520 plus this 2537k. So which means this is the answer.